Ever sit at your desk and suddenly your speakers start making this weird rhythmic buzzing sound right before your phone lights up with a text? It is a tiny, everyday glitch, but it points to a massive engineering challenge. It is the exact reason why every single piece of electronics you buy, from your Wi-Fi router to your kitchen microwave, has to pass strict government testing before it ever hits store shelves. The culprit is EMI, or electromagnetic interference, simply unwanted electrical noise. This stray energy spills out of devices in two ways: conducted along physical cables, or radiated through the open air, like an invisible radio station. Because this noise is everywhere, engineers have to design devices with a specific goal in mind: EMC, or electromagnetic compatibility. A compatible device works perfectly without causing hiccups in nearby equipment, and without being bothered by the noise around it. Think of this as a good neighbor policy for electronics. First, control your emissions, like keeping your music down to not bother neighbors. Second, you need immunity, like wearing earplugs to sleep peacefully while someone vacuums. So EMI is the interference, the noise problem we have to deal with. EMC is the engineering goal. It is the state of peaceful, stable coexistence between devices. Achieving that stable coexistence is vital today. As we rely on 5G networks and delicate wireless devices, the airwaves are more crowded than they have ever been. This chart shows exactly how interference ruins a wireless connection. The green line is our clear, useful signal. The red area at the bottom is the noise floor, the baseline level of unwanted energy in the environment. Think of trying to have a conversation in a quiet coffee shop versus a loud rock concert. As the background noise gets louder, the red floor rises, shrinking the gap between your signal and the noise. Eventually, the signal gets completely swallowed, and communication drops. The sources of this rising noise floor are often right inside the devices themselves. High-speed signals and power modules, which rapidly flick electricity on and off to stay efficient, can cause the tiny copper pathways on a circuit board to act like accidental antennas. A dropped Wi-Fi call or a blurry video feed often traces back to a physical layout mistake on the circuit board, allowing noise to leak out and drown out the connection. To prevent that from happening, engineers rely on 5 primary techniques. It is essentially a toolkit for soundproofing their hardware designs. The first tool is shielding. By placing a physical metal barrier or enclosure over a noisy component, we can trap the radiated energy inside and keep it from broadcasting through the air. The second tool is filtering. A filter acts like a bouncer at a club. It lets the clean, useful frequencies pass right through, but it turns away and blocks the unwanted noise. Tool number 3 is grounding. A proper ground provides a safe, direct path for stray electrical currents to flow back to their source. It acts exactly like a storm drain that safely funnels away heavy rain before it causes a flood. Fourth is the layout of the printed circuit board itself. By keeping copper traces short and carefully stacking the layers of the board, engineers can prevent those internal pathways from ever acting like antennas. Finally, there is cable management. Twisting pairs of wires together or wrapping individual cables in their own metal shielding stops them from picking up noise or radiating their own. Achieving a quiet device requires specific physical choices during the design phase to build a protective wall around the sensitive electronics. Once a device is built, engineers have to prove those choices actually worked. A company cannot legally sell a new piece of hardware until it passes strict, specialized testing. In professional labs, engineers measure a device's emissions and perform immunity tests by blasting it with interference. They use massive rooms lined with foam spikes, anechoic chambers, to block external waves, ensuring they only measure the device itself. These highly controlled environments enforce strict legal limits set by international groups and government agencies, like the FCC in the United States. If your product generates too much noise, it cannot be deployed. We've covered a lot of ground, but the core concepts are straightforward. EMI is the inevitable noise problem, EMC is the goal of operating peacefully, and physical design techniques form the bridge between the two. Whether you are setting up a complex radio receiver on your desk or just trying to get a reliable Wi-Fi signal in your living room, these principles dictate how well your gear performs. The invisible world of electromagnetic energy is naturally chaotic and crowded. But through careful, disciplined engineering, we can manage the noise and keep our connected world running smoothly.